About a year ago, I talked about the Gauss-Bonnet theorem, how it allows to compute things quickly. And I'm a big fan of the paradigm simplicity, clarity, and generality, and especially simplicity. And also the simplest solution is usually the best one, as Occam's razor. So I want to illustrate this in the context of this fusion problem I'm still working on. And you might wonder, that's a complicated thing, but it's actually only 6 lines of Mathematica code which generates you from a general arbitrary abstract simplicial complex, or even an open set generates you the cohomology. And that's these are the experiments I have been doing, and we see this beautiful relation between so you have an open set U open and K is U complement, then the Betti number of U plus the Betti number of K is equal to the Betti vector. This is the Betti vector then, so B is B0 until BD. So these Betti vectors satisfy, and that's the interaction cohomology. Still not proven that BI. So we need that the map, there's a map which gives us here from the cohomology groups H U plus H K, that goes to H G, and that should be surjective. And so that we have then a short exact sequence. So that's the fancy way to express this. This is a Meyer-Wheat race. And the picture which we had is actually kind of that was K, and that was the closed set, that's the open set, and we put it together and we get the G. So in this case what we have is 1, 0, 0 plus 0, 0, 1 is equal to 1, 0, 1. So I talked about this a couple of times, and I would really like to show that this is surjective. So meaning that if I take a cohomology class here and a cohomology class here, I fuse it together, and then I let it flow with a heat flow. So that's the heat, you can apply the heat flow here, and then you get a cohomology class in G. And I want that to be here, or they get killed and annihilated, these kind of particles get annihilated, and that really happens if you have here a Möbius strip, and then you attach, if you take a Möbius strip, Möbius, and you attach to the Möbius strip an open ball, because you attach to the boundary, right? So that's the boundary is just a circle, then you get P2. In this case, there is this cohomology class. When you apply the heat flow, gets destroyed here. And this one, the one form cohomology, in the first cohomology, because this is a kind of a circle, you also gets destroyed, and we want to understand this. So if I call this G, this is my simplicial complex, and I say I want to have a basis of G, so I get the, so you see kind of these are all the open sets in this star graph. It's here. So the open sets, this is an example of an open set. So this is U of 1. But there are other open sets, and just making another one. There are other open sets, like star of that point here. It just contains the point and everything which is containing that point, which in this case is just an edge. So these are all, this is the topology here. So this is the basis for the topology, and I could generate the whole topology if I wanted, and can also generate random open sets in this complex. And now, if we have an arbitrary set of sets, we can look at this. We have an exterior derivative, which is the usual definition of exterior derivative. I like to define it really with just embedding signature, so that we don't have to kind of delete entries, etc. What we have here is a little bit of code. So signature of X, first of all, if I have we just show that kind of S. First of all, we have to understand S. So I take a permutation like 1, 2, 3. That, of course, has S equal to 1. If I switch to 3, 2, then I get -1. Now I can also look at that. So I can say, oh, how is 3, 2 embedded in that thing? So that's embedded with embedding signature 1. But if I take, for example, 2, 3, then I would get -1. I would also say if I take 1, 3, so that's 1, but 3, 1 is equal to -1. Or I can look what happens when I take 1, 2. So that's -1. And then from that function, essentially that's already the exterior derivative. We have then the Dirac operator. So for example, I can say, so let me just make maybe a little bit larger thing. So maybe the wheel, I take the wheel graph with maybe 7 elements. Now I have the G, and I can say, okay, what is the Dirac of G? I made it such that it also gives me the block sizes. So I just take the first element of that is actually the matrix itself. So that's the matrix, and I can plot that. So I call this maybe B, and then I can plot that matrix plot of B. So this is this Dirac operator. So it's a self-adjoint matrix, and if I take the square of that, so if I take the square of that, B times B, then I get the Hodge. So that's the graph we have. This graph contains, it's a simplicial complex, defines a simplicial complex which has 25 elements. So there are 7 vertices. There are, we have counted it here with the F vector, there are 12 edges and 6 triangles. So if you look at that, so there is 7, that's the first block. That's actually nothing else than the Kirchhoff matrix, and then the next block and thing. So now we are talking. So this is the 5, 10, 10, 5, 1. This is the F vector of this now three-dimensional sphere. I can also look what happens with Betti of that H. So that's thing. So that's 1, 0, 0, 1. That's the Betti. This is the Betti vector of a three-dimensional sphere. So Euler characteristic is 0. I can take random example. I can make experiments. I can say, okay, G is my, so maybe a random graph with maybe 10 vertices and 20 edges. Let's just take that. So that's a random graph. And then I take G is the Whitney complex of G. So that's what I can do. So I have the Whitney complex, and now what I can do is I can just take a random open set there. So I call this U is a random open set G. You know, I just take 3 elements of the basis and add them up. So maybe 3, and so that's the U, and then I take K is the complement in G of U, so that's a closed set, that's a simplicial complex, and now I can compute all these pad right, because they have different size, so it doesn't know if I compute the Betti vector of some smaller dimensional part, the vector might not have the same length, so I have to take pad right of that. So now I have vectors which have the same length, and I take now A plus B minus C. So that should be something non-negative. And so in this case, this is the interaction cohomology BI. So it's very interesting that we have still kind of something which sees here. I mean, it's not surprising. Like in this example here, we see that I have a different cohomology. There is something happening when we glue things together, and I like to think about this as kind of just maybe there's a proof showing that I take here harmonic forms. So that's what I tested also. I just took harmonic forms here and let them flow with the heat flow. That gives us a harmonic form in G. Gives me a harmonic form in G, and then hope that I can really get everything like that. And so we have a particle here, we have a particle here, we put them together, they live on the larger space, and in some sense what happens is they can only get annihilate each other. Something cannot be created additionally. So that's what this means here. The BI bigger or equal to 0 should be a cohomology, should be a non-negative. And that's what I see here. So I can make these runs, right? I can make as many runs as I want. In this case, I had even 2 particles, 2 1 forms and 2 2 forms, poof, which went down the drain, right? What happened with the Betti U was here this, and the Betti K was this, and the Betti G was this in this case. So what happens is the Betti number here plus the Betti numbers here don't add up exactly, but there is something which has been destroyed, and that's this interaction. That's this interaction cohomology. It's very exciting, and I still need to think about this more. Why is this surjective here? That's it.